Hi, this is Stephen, and in this video we will look at further application of the simplified Bernoulli equation to look at valves. And just to review, in our previous video we talked about how if you have a valve with blood leaking backwards, and you want to know the difference in pressure from the high pressure to the low pressure, we discussed how you can say that the high pressure minus the low pressure equals 4 times the velocity of the regurgitant jet squared. Well, it turns out you can use the same principle with a stiff valve. So now I'm going to draw a valve that is barely opening. And again, you have blood that is rushing through this narrow point, going from an area of high pressure to an area of low pressure. And again, we can actually use the modified Bernoulli equation to say that the peak gradient between the high and low pressure is equal to 4 times this velocity through the stenosis, that Vmax squared. And so how do we use that practically? Well, let me draw out our apical 4-chamber view. So this is your left atrium emptying into your left ventricle. Over here you've got the right ventricle and RA, and we've tipped it to the so-called 5-chamber view where you can see the LVOT, the aortic valve, and we are measuring the velocity through here with our continuous Doppler, and you'll get something like this. And let's say that this Vmax equals 4 meters per second. This units here, this would be second, and this would be meters per second velocity. So you get this velocity. The question is how we can go from a velocity to estimating a peak gradient across that aortic valve. And you might wonder, how do I know it's exactly across the valve? Well, again, continuous wave Doppler measures all the way along this dashed yellow line, but the maximum velocity will be wherever the narrowest flow, the narrowest path is for blood to flow. So that's typically at that stiffest point of the valves. And so if let's say I define this area right here, we'll say that this is the area of high pressure, and this somewhere down here is the area of low pressure. We can say that the high pressure minus the low pressure is equal to, that is equal to 4 times the velocity max squared, which in this case, 4 times 4 squared, 16, that would equal 64. So 64 millimeters of mercury would be the peak gradient across this aortic valve. Now, just note that the computer can actually look at the integral, the VTI, and the computer can actually, with its own formula, figure out a mean gradient. And actually, with stiff valves, we typically use mean gradient rather than peak gradient. The math on that's a little more complicated, so we won't go through that. But just like we can calculate the peak gradient, the computer can calculate the mean gradient through looking at all the different values of velocity, not just the maximum velocity. But that's how we do. That's how we can go from a velocity measurement to a pressure gradient across a stiff valve, and we can use that in other valves as well. I guess before I go through that, though, let's say instead it was more of a normal valve, and we actually measured something like this, where it was just 1 meter per second was this peak. What would that correspond to in terms of a pressure difference? Well, in that case, you would say that P high minus P low equals 4 times 1 squared, which is 4. So there's a very trivial difference between the high and low pressure areas, as we would expect. Now let's look at some other stiff valves. We can look at stiff or leaky valves. Let's turn to a view we haven't looked at in a couple of videos. Let's look at the parasternal short axis view. You've got your aortic valve, and then over here you've got your right atrium, your tricuspid valve, you've got your pulmonic valve, left atrium back here. I can take my continuous wave Doppler trace and I can measure right back here. Or to get the gradient across the tricuspid valve. Or I could measure right back here and I could get the gradient across the pulmonic valve. And the same thing, if I look at here across the pulmonic valve, I'll get some kind of a trace, and I can take that Vmax, and if I go 4 times that Vmax squared, that will give me the peak gradient across the pulmonic valve. Similarly, if I look over here from the tricuspid valve, I'll get something like this, and if I take 4 times that Vmax squared, that will give me the peak gradient across the tricuspid valve. If I'm looking at tricuspid regurgitation, that would be something going down this way. That's what we talked about in the previous video. I can take 4 times that Vmax squared to estimate the pressure difference between the right ventricle and the right atrium. So in this video, we've just discussed how, just like you could use it with leaky valves, you can also with stiff valves use the same principle that if you have blood flowing from an area of high pressure to an area of low pressure through a narrow orifice, if you can figure out the velocity in that orifice through a continuous wave Doppler, 4 times that velocity squared, that gives you your peak difference in your peak gradient, the high pressure minus the low pressure.